Let's continue into the directional variography. For this data set, because it's a dense data set, we are going to be trying to infer the directions of anisotropy directly from the data. For that, we need to specify the lag distances. We already saw how to specify lag distances. In this case, we are using lag size of 5, a lag tolerance of 5, and we're calculating the variograms for 10 lags. Because of this tolerance, which is equal to the lag size, we are going to have some overlap between the experimental points. Next, we are specifying the variogram searches. We saw before the use of xpvario search. In this function, we would be required to provide one azimuth, one inclination, the lag distances, and then the tolerance parameters. You'll see that we are now using a specific method, and this method is called a sphere. You will see that we no longer need to specify a single azimuth and a single inclination. Instead, we have to define the number of directions that we want to consider. So this method is gonna create automatically as many directions as I specify in here. The default value is 40. That evenly samples the 3D space. So it will create 40 different directions in the 3D space that we are going to calculate the experimental variograms for. So we provide the lags to this function, and we are going to use the defaults for every other argument. With the searches defined, we can go ahead and calculate the experimental variograms. We are going to use the same class as before, rmsp.xpvario. We're going to use a pairwise relative variogram type, and we're going to use the method calculate, provide the composites, the variable, and the variogram searches. Once we run this part of the cell, it's going to calculate the experimental variogram for all the 40 directions, and then we move into fitting these experimental points. For this example, I'm going to split the calculation into a separate cell, and we can go ahead and calculate the variogram. If you want to look at all the different directions that we are considering for this experimental variogram calculation, you can take a look at the searches object. The searches object is a list of 40 different xpvario search objects, and each one of these have a different azimuth and inclination. And this azimuth and inclination is a even sample of the 3D domain. Now that the experimental variogram is calculated, we can move into the variogram fitting. We saw this class before for fitting a omnidirectional variogram, but for the directional variography, we need to be a lot more careful because we are now fitting the directions of anisotropy. The number of structures that we have selected for variogram fitting is 3. We are passing the experimental variogram points that was calculated in the previous cell to this function. We are fixing the nugget to what we defined previously. We are also fixing the shape to be the same shape that we used to visualize the nugget fitting, which was exponential. We're defining the number of structure to be 3. Now we are specifying some manually defined restrictions to some of the variogram parameters. Starting with angle 1, we are restricting the angle 1 to be between 240 and 260. And we are restricting the angle 2 to be between -50 and -70. The number of structure here is used to multiply these restrictions because we want to use the same restrictions for each one of the 3 variogram structures. We could define different restrictions for each variogram structure, but in this case, we are just using the same restriction for all the structures. Angle 3 is restricted to 0. Range 1 is restricted to be between 5 and 4,000. The anisotropy ratio between angle 1 and 2 is restricted to be between 0.9 and 30. And the anisotropy ratio between range 1 and range 3 is between 0.9 and 30 as well. The output of the variogram fitting is captured into this VarioMod object. In order to visualize the quality of the fitting, we are using our experimental variogram with the method gridplot and providing the model VarioMod to be added to the plots. This grid plot is used to plot many directions at once. In our case, we specified that we wanted to calculate the experimental variogram for 40 different directions. So the grid plot method is going to create a grid of multiple experimental variograms with all the 40 directions. And lastly, we are looking at the fitted variogram parameters in a table format. Let's run this cell. The fitted variogram parameters are shown in this table. You will see that all the restrictions that we specified for the fitting are met. The angle 1 is between 240 and 260. Angle 2 is between -50 and -70. Angle 3 is set to 0. Nugget is set to 0.11. And the largest range 1 is set to 4,000. And we do not get higher than 4,000 for range 1. So everything is within expectation. We can also see the plots. So all the 40 different directions for experimental variograms are shown here, and the curve for the fitted model is shown in orange. Let's see what changes when we change the fitting parameters. So for this experiment, let's keep the original plot and take a look what happens if I set the number of structure to 1 and perhaps remove some of the restrictions. Now we only have one structure. Our angles are unrestricted, our ranges are unrestricted, and this is the fitting that we get. So we can compare the new fitting with the old fitting. Let's get back to the original parameters.